Alright, here we go again. Today we're dividing by polynomials. Actually, we're taking this section and breaking it up into two pieces. Our first piece here, 4.4, we will, in this section we will consider dividing by a monomial, just single terms. And in the next one we'll take it up a notch. On 4.5 we'll divide by binomials and trinomials and any general polynomial. So this is the easy part of dividing by polynomials, where we just concentrate on monomials. It goes something like this. No one should be dividing by anything if they don't have a clear definition of division. It should be really outlawed. It should be a law. Nobody should be dividing if they don't understand what dividing means. So we're going to try to get a powerful definition of divide. For us, we will handle it in the same way that we did subtraction. The way we handle subtraction is we exchanged it for additions. All our subtraction problems we could change into addition problems. We're going to do exactly the same thing for division, and we're going to take that as our definition. It goes like this. To divide means to multiply. To divide by b means multiply. Multiply by the inverse of b. That is the multiplicative inverse. It might seem strange to you, but it has a lot of powerful ideas. Division is not commutative. Multiplication is. Division is not associative. Multiplication is. You can get with this or you can get with that. All the rules that we learn, all the powerful axioms, they work for multiplication, and none of them, or hardly any of them, work for division. That's why we can. This is a powerful definition. Every one of these division problems we can change into just a multiplication problem. We multiply by the inverse. It might seem strange to you, but it's really not. It's completely analogous to what we did with subtraction. Every subtraction problem can be changed into an addition problem. To subtract b means to add inverse of b. Okay. Every subtraction problem, change it to addition. Adding the inverse. Division means multiply by the inverse. So on with that. What does that mean for our problem here? This means that if this is your given problem, you could rewrite that as 21 times 1 over 3. That's the definition of divide. And of course here you can go many ways to proceed here. One way would be to just write this as 7 times 3 times 1/3. This would be by times table. And this would be, I can reassociate these. This would be 3 times 1 over 3. That would be the associative law of multiplication, and of course that would be 7 times 1. And of course that would be by multiplicative inverses, which would give you a total of 7 by multiplicative identity. Yippee-ki-yay, perfection and beauty and creativity and reasoning like you've never seen before. Perfect steps. This sort of stuff we've done before though, so we can package all this. We can do this by inspection. So an alternative way would be to say 21 divided by 3. Here we go again. Watch this. This means 21 times 1 over 3 by definition of this, and this would be of course 21 over 3 by definition of a fraction, and I could just say, well, that's equal to 7 by inspection. So here's another way to do it. Okay, just a little tiny taste of division, but this is an extremely easy problem. So what we've got to do today is focus on polynomials. So let's make some progress in that direction. Here's some progress in that direction. Sometimes you'll have more than one term that's being divided by a monomial, and let me see if we can tackle that in a couple different ways. Just to show you one way to do it, we could say this is 21 plus 30 plus 9. This could be times 1 over 3. Why? Because every division problem by definition is really a multiplication problem. You can multiply by the inverse. And so this would, then I could distribute this, and this would become 21 times 1/3 plus 30 times 1/3 plus 9 times 1/3, and this is by the distributive law. Okay. So I took this 1/3, and there was 3 terms in here, 3 terms, and I distributed to that one, to that one, to that one. That's what you get by the distributive law. And then of course you could proceed here. This would be 7 plus 10 plus 3. And this is by inspection, which is clearly 13 plus 7, or sometimes people would say 20. And there you go. There's another way of looking at it. This one's kind of nice because it gives you insight into what we're going to do today. Today we're doing polynomials, and so I've written this as a sum of terms on purpose, just so that you could see how we can distribute that. I know you could distribute this, but that would hide the patterns. That's not what I want to do. I want to illustrate how this stuff's going to work when you have, instead of having 21, you have some polynomial, some monomial there, monomials there, and all these numbers could be monomials. The procedure though is still the same. You should feel comfortable doing it this way. Also, you could add this together. That of course is 21 plus 9 is 30 plus 30 is 60. 60 divided by 3 is 20. Another way to do it. Okay, that's one more chance to get here comfortable with division. This means 21 times 3 over 5. That's the definition of divide. Means multiply by the inverse. It might take you a little bit of time, but you know the inverse of 5 over 3, the multiplicative inverse would be 3 over 5. And then of course I could say this is 21 over 1 times 3 over 5. This is by the 1 under theorem. And of course I could multiply across if I wanted. That would be 60. 3 by mat. And there you go. Another division problem. Alright, but enough of this. What we really want to focus on today is polynomials. So come back and for the second part of this, and we will start dividing by some monomials. Okay, we'll see you guys here in just a bit. So here's the most basic division problem for polynomials. It would be a monomial divided by a monomial. And I want to take my time with this and show every single step with unapologetic perfection. This would be 21x to the third times 1 over 15x squared. That's by definition of divide. That's what that divide means. It means multiply by the inverse of that. Then I could say, well, this is 21x to the third over 15x squared. That would be the definition of fraction. Says you can bump this one up there. And now you can just reduce the fraction. Fortunately for us, we took a lot of time to develop the ideas to perfection when we did the fractions with regular numbers, to where we can apply those ideas to this place in our course now. In fact, you can apply those ideas to all the places in all your courses. What I'm trying to say is that we've already done all the heavy lifting here. We already have all the perfect ideas. Let me remind you what they were. The ideas that we used here that will help us would be prime factorize the top into the prime pieces, prime factorize the bottom into the prime pieces, and then see what's common. What's going to be common would be the GCD. We can cancel that. We can unglue it using math and kill everything by jot. As easy as it sounds, that's all you got to do. So let's do it. Prime pieces are 3, a 7, an x, and an x on the numerator, a 3, a 5, an x, and an x on the denominator. That's just prime factorizing it so I can see what the prime pieces are going to be. Let me switch off to another color. Let me see, blue. Can we do blue? See, this is going to be common, an x is going to be common, another x is going to be common, another 3 is going to be common. And that's as much as it's going to be common. So I'm thinking here that the GCD between the numerator and denominator is going to be 3x squared. That's what I'm going to be able to cancel. And I can see what's going to be left over when I do that. There's going to be a 7x over 5, and that will be my final answer. Of course, talk is cheap, so let's do it. So I'll show it like this. 3 times x squared times 7x all over 3 times x squared times 5. This is just rearranging them. You could say this is by commutativity, associativity, a bunch of things from last few months of our course. Now I can unglue this using math backwards. That's multiply across theorem. And now it looks nice. It looks like this. And you see this is just one. That's just one theorem. Any number over itself, as long as it's not 0, infinity, or anything weird, will be just 1. The 1 times anything does nothing. The 1 is like water, so you get 7x over 5. And now right there, you can barely see it, but you can see enough to see the beauty. This is how we would do this step by step, showing every single part of the reasoning. Now in practice, what happens is in practice, people don't do it this way, or by now you should feel comfortable with all these steps where you can do a lot of these by inspection. So you might be okay, I think, by now if we try something like this. If you get to this step right here and you can say, you know what, I think I could do this by inspection. I'm going to cancel the x's and the x's, and this is just I'll just have a 7x left on the bottom, on the top, and a 5 on the bottom. That will be okay too. Okay, that would be the by inspection way. If you're comfortable with all the steps, this would be good for you. If you're not, you need to practice those steps. Okay, this is the easiest possible scenario. Where could we take it from here? Well, we can only take it up from here a few notches. Let's take it up on a few notches. How about a polynomial with 4 terms divided by a monomial? Again, I'm going to go 2 different ways on this one, because the more ways you know, the better, the more powerful you're going to be. Okay, you don't want just the answer in the shortcut, right? Time is gone when answers were of any valuable. Answers are useless now. Powerful thinking is useful. So I'm going to give you 2 powerful ways to think about this. First way would be like this. You write, I'm going to go with yellow. Yellow's mellow. 21x to the 4th plus 12x to the 3rd plus 15x plus 2. I'm going to go with that times the inverse of that. That's the, there I go, getting rid of our division, because divisions are useless. We can change them all to multiplication. And now I can use all my powers here from multiplication. I can distribute. I have 4 terms in here. You see, they're all separated by plus or minus. So this one can be distributed to all 4 items. So that would be 21x to the 4th all over 3x plus 12x to the 3rd all over 3x plus 15x all over 3x plus 2 over 3x. This is by distributive law and definition of A over B. And now what I have is 4 of the little baby problems of the type that we just got done doing. So each of these you could do by inspection. 21 over 3, that would be 7. 7x to the 3rd. Again, if you have trouble doing that, you should prime factorize the top, prime factorize the bottom, and see what's common. Here I would have a 4x squared. Here I would have a 5, and here I would have a 2 over a 3x. And that would be one way to carry on the division of a polynomial divided by a monomial. And this is just change it into times, distribute it into a bunch of little tiny fractions, and handle each of these little tiny fractions separately. Okay, that was so fun. We should try the same problem, but we should do it a different way. What if we tried something else? And for that, let me take you back to some things from your childhood here. Do you remember when you were a kid and you divided some number, for example 2019 divided by 5? Back when you were in grade school, you might have done something like this. You would place the 5 over here, and you would place the number here, 2019, and you would try to focus on the leading terms. For example, the 5 and the 20, and you would ignore everything else and just focus on the 5 and 20, and ask yourself, oh, how many times will it go there? And you'd say, oh, it might go 4. And after you figure that out, you would multiply the 4 times the 5, and you would write it beneath here. And after you did that, you would probably, whoa, that was unintended. After you did that, you would, that was also unintended. You would subtract this and say that would be 0, and then you bring down the next one, and you'd ask how many times does 5 go into 1? Well, it doesn't. Then you would bring down the next one. And so you'd go, maybe it goes 3 times, and you'd go, okay, 3 times 5 is 15. Then you change the sign and you get subtract them or add once you've changed the sign. And so you'd say, okay, that's that plus the remainder of 4, which would give you 4/5. That process right there of dividing is called long division. We're going to resuscitate it today, and we're going to apply it to our polynomials. So take this problem, the one we did 2 seconds ago, and let's see if we can do it the same way, or do the same problem but now using long division. So long division might look something like this here. It might look like this. You put the 3x on the outside. That's the thing you're dividing by. That always goes on there. They're not interchangeable. Division is not commutative, so order does matter a lot. This one goes out here, this one goes inside. 21x to the 4th plus 12x to the 3rd. Sometimes you may want to use placeholders. Sometimes they're useful. Like if I have, see, this is degree 4, degree 3, degree 1. The degree 0 is skipped in there, so sometimes it might be helpful just to keep things organized to put a placeholder 0x squared plus 15x plus 2. That's optional. And you focus on the leading terms. How many times will that one go into that one? 3x, and you think, well, to do that, you could make sort of a thinking bubble here and say, you know what, I gotta think, what I have to think about is how many times will the 3x go into the 21x to the 4th? And the answer would be 7, 7x to the 3rd, 7x to the 3rd, and I usually try to keep them lined up. You could put the 7x anywhere, but if you line them up in the columns where they go, you'll see that by the end of your problem you'll have something that's really nice, or semi-organized. This will be 21x to the fourth. After I've multiplied it, 7 times 3 is 21, x to the third times x is x to the fourth. Subtract it and you get 0 x to the fourths. That's nice. That's what's supposed to cancel. That's what's supposed to happen. You cancel the leading term. You bring down the next guy, and now you start the process all over again. And you ask yourself, how many times does this one go into that one? You might say, well, again, if that's too hard for you to do in your mind, you can feel free to make a little thinking bubble. You're asking yourself, how many times does the 3x go into the leading term, which is a 12x to the third? By the way, you can always bring down the rest of them if you want. Bring them all at once. This is your problem now. Or you can just bring that one. Doesn't matter. So the number of times that will go in there would be 4x squared. So I put it here, 4x squared on top of the x squared column. Then I go in and I multiply that. That gives me 12x to the third. And then I subtract the sign there. And I start the process all over. This gets killed, and so I have 0x squared plus 15x plus 2 left over. And now I start the process all over again. And I ask myself, how many times will the 3x go into the 0x squared? And the answer would be 0. 0x's. That would give me 0x squared. I subtract it, and I start the process all over again. Now I ask myself, how many times will the 3x go into the 5x? And of course that would be 15x, I meant 5. So then you take the 5 and you multiply it. That gives you 15x. Then I subtract it. And then I bring down the next guy. And you start the process all over again. And by now my remainder here is smaller than this one. The way you can tell whether something's smaller or not is you look at the degree. This has no more x's, so it's degree 0. This one is degree 1. So that's already smaller, so it's a remainder. 2 over 3x. And that right there is our answer. Using long division. Okay? It should be the same answer that we had before. Where was it? Using our previous technique. Yeah, maybe. Oh, there we go. There we go. 7x to the third. 4x squared 5 and 2 over 3x. That should match the same thing that we just got right now. 7x to the third, 4x squared 5, 2 over 3x. Alright, that's how you do long division. One more time. Let's try it now on this problem. Let's try it on a different problem. 20x to the third, 12x squared, 16x, and that divided by 4x. So here's what you do. You write the 4x on the outside. You write all these things in the inside. I try to keep things organized by columns here. My degree 3 column, degree 2, degree 1, degree 0 column. And see how it goes. First I just focus on the leading terms. That would be 5x squared. That will give me 20x to the third. That gets cancelled when I change the sign, so forget about it. And now I bring down the next one, 12x squared. Well, I bring down the rest of it. And I start the process all over again. So I focus on the leading terms. How many times will 4x go into that one? That would be negative 3x. I multiply it, I get negative 12x squared. I change the sign. When I change the sign, that would become positive. And then I bring down the next one, and I start the process all over again. Now I got to figure out how many times will the 4x go into the 16x. I'm going to think that's 4. That'll give me 16x. Change the sign. Add these down. Once I've changed the sign, I can add. 3 is already smaller than that one, so that's my remainder. Negative 3 over 4x. That's dividing a polynomial by a monomial using long division. You may not prefer this. The other way that we did it at the beginning was breaking it up into little fractions. But there's a very important reason why we do it this way, because in the next section we're going to be dividing not by monomials, but we're going to be dividing by binomials and polynomials. And to do those, this may be your best way. According to 5,000 years of research and all the algebra teachers that have ever lived, this method, the long division, may be one of your best options when you're dividing by a polynomial or monomial. No, sorry, polynomial. actually your best option is just to cheat and do it on a calculator. But if you're going to do it by hand, this may be the best way. And it's also good for understanding too. It gives you a chance to review your grade school years when you were doing this with regular numbers. Alright, I think we'll stop here. Now your turn to do a bunch of these for practice. We'll see you guys here next time. Peace.
I'll do it.
Go.
Peace.